You pour a drop of ink into a glass of water. Within seconds, it spreads, twisting and curling, until the entire glass turns a uniform blue. Nothing unusual, right? But here's the puzzle. If every single molecule follows reversible laws of motion, why can't we just rewind the system and get the drop of ink back, untouched, floating again in clear water? This is the irreversible mixing paradox, and it challenges something very basic. If the underlying physics allows for time to run backward, why does mixing always feel like a one-way street? In this video, we look at why mixing seems permanent, even though the motion of each molecule could, in theory, be reversed. From dye filaments in gentle fluid flows to the mind-bending complexity of microscopic chaos, we explore how tiny uncertainties and countless particle interactions pile up to make unmixing practically impossible. The laws of motion may be time-symmetric, but once entropy starts to rise and probabilities take over, the game changes. This paradox shows how nature favors disorder, not by breaking the rules, but by following them in ways we still struggle to fully grasp.
Irreversible mixing paradox. How does the spontaneous mixing of two fluids challenge the idea of reversibility in microscopic dynamics? And why does the process of mixing appear irreversible even though the individual particle motions are governed by time-reversible laws? Fluids are known for their ability to mix. Place a drop of dye into water and it rapidly disperses, transforming into a seemingly homogeneous blend. Classical physics tells us that the microscopic equations of motion, whether Newtonian or quantum, are reversible. If you could reverse all particle motions perfectly, the system should retrace its steps and unmix. Yet in practical terms, once two fluids mix, they never simply separate into their original pristine states. So far, so good until we look closer. The irreversible mixing paradox arises when the elegant symmetry of time-reversible microscopic dynamics collides with the overwhelming complexity of macroscopic processes. Under ideal conditions, if every fluid molecule's velocity were reversed with absolute precision, the original configuration of unmixed fluids could, in principle, be restored. However, when two fluids interact, the process quickly gives way to an inexorable spread of molecules, an irreversible journey toward increased disorder and entropy. One striking example comes from experiments in fluid dynamics, where a drop of dye introduced into a gently stirred fluid stretches into fine filaments. These filaments seem to suggest an underlying order. If the stirring were exactly reversed, the dye might coalesce back into its initial drop. But in practice, the tiniest imperfections and minuscule perturbations during reversal ensure that this precise unmixing never occurs. Even in laminar flows where the motion is predictable and smooth, molecular diffusion, a random, irreversible process, eventually homogenizes the fluid, defying any attempt to revert back to the original separation. At even smaller scales, the story grows even more intricate. In systems with a vast number of interacting particles, the possibilities for each molecule's position multiply astronomically. What should be a neat retracing of paths transforms into a statistical avalanche. The mixed state corresponds to an overwhelmingly larger number of microscopic configurations compared to the separated state. The reversible nature of each individual collision becomes irrelevant when considered against the background of an almost infinite array of possibilities. Here, the increase in entropy, a measure of disorder, imposes a macroscopic direction to time. The arrow of time relentlessly points to mixing and disorder. And then there's the matter of sensitivity to initial conditions. In any real-world scenario, even the slightest error in tracking the positions and velocities of every molecule prevents the perfect reversal needed to unmix the fluids. This chaotic behavior ensures that any attempt to reverse the process results only in further dispersal, rather than a return to the original ordered state. Even classical engineering fields grapple with this paradox. In microfluidic devices, for instance, the manipulation of fluids in tiny channels might suggest the possibility of precise control and even reversal. Yet, when molecular diffusion and thermal fluctuations come into play, the inherent irreversibility of mixing imposes strict limits on the ability to separate fluids once they have blended. As we design ever more precise systems at miniature scales, these irreversible processes reveal the limitations of our classical approximations. So what's really going on? The paradox lies not in a breakdown of microscopic physics, but in the limits of applying those time-reversible laws to systems with staggering complexity. The idea of reversible mixing stems from simplified models that assume perfect control over every interaction and neglect the statistical nature of large ensembles. In reality, the sheer number of particles, coupled with the probabilistic character of thermodynamic behavior, ensures that macroscopic mixing is effectively irreversible. It turns out that while individual molecular collisions are theoretically reversible, the collective behavior of countless particles is governed by probability overwhelmingly favoring the high-entropy mixed state. Mixing doesn't just happen on the surface. The process is a profound manifestation of how microscopic precision is lost in the chaotic, high-dimensional dance of molecules. The irreversible nature of this process reminds us that nature often refuses to be confined by our idealized equations. The irreversible mixing paradox is a reminder that our intuition, rooted in the reversibility of isolated particles, fails when faced with the messy, entropic reality of complex systems. It invites us to rethink the relationship between microscopic order and macroscopic chaos, and to appreciate how the inexorable increase of entropy shapes not just our theoretical models, but the very fabric of everyday phenomena. The irreversible mixing paradox unveils a striking contradiction. While the microscopic equations that govern fluid particle dynamics, be it classical mechanics or quantum mechanics, are inherently time-reversible, the macroscopic process of mixing two fluids appears to be one way. When two distinct fluids come into contact, their molecules interdiffuse until they form a homogeneous mixture, a state that cannot simply be reversed by retracing the molecular paths. Example, consider a drop of ink dispersing in water. Each ink molecule follows a specific reversible path in principle. However, the overall result is a uniformly colored solution that resists any attempt to restore the original concentrated drop. Analogy: it's like shuffling a well-ordered deck of cards. Although every move is reversible, once the cards are thoroughly mixed, restoring the original order is practically impossible without an extraordinary precision. At the heart of the paradox lies the contrast between the predictability of microscopic dynamics and the emergent behavior at a larger scale. In theory, reversing the motion of every molecule should lead to the initial segregated state. Yet, in practice, once fluids mix, the process appears to be irreversible. Example, when cream is stirred into coffee, the individual molecular motions are entirely reversible by the fundamental laws of physics. Nevertheless, one does not observe the cream naturally separating from the coffee. Analogy: imagine a perfectly executed dance routine where each step can be precisely undone. In reality, if a crowd spontaneously joined the routine, uniting into a single mass, it would be near impossible to retrace those steps exactly and separate each dancer into their original formation. Every molecule in a fluid follows deterministic and time-symmetric rules. However, the sheer number of particles and the chaotic nature of their interactions lead to a collective behavior that defies simple reversibility. The reversible trajectories of individual molecules collapse into a macroscopic irreversible phenomenon when viewed statistically. Example, in a high-precision computer simulation, if one were to reverse every individual velocity of fluid particles, the system could, in theory, return to its starting arrangement. However, any minute deviation, impossible to eliminate in a real-world scenario, disrupts the reversed pathway. Analogy: think of an enormous mosaic made up of countless tiny tiles. While the location of each tile is precisely determined, disturbing even one tile changes the overall image in such a way that restoring the original becomes practically unfeasible. The process of spontaneous mixing is driven by diffusion and chaotic advection. Even when the molecular motions are theoretically reversible, the combined effect of countless interactions results in a steady progression toward a state of uniformity. This evolution is not due to any inherent asymmetry in the laws of motion, but rather The statistical inevitability of disorder. Example, when two colored fluids are placed in contact within a container, the tiny fluctuations in velocity and position lead to an incessant gradual blending, even if every individual collision could be reversed. Analogy. Consider a drop of food coloring dispersing in water. While each colored molecule may follow a reversible path, the collective behavior is analogous to countless droplets merging into an unrecognizable whole. A diffusion that practically locks in disorder. Trippy, a measure of disorder, plays a pivotal role in the irreversible mixing paradox. Although every microscopic process is reversible, there is an astronomical disparity in the number of configurations available to a mixed state compared to a separated state. As a result, once fluids mix, the system naturally evolves towards a higher entropy state where the original configuration is overwhelmingly unlikely. Example, in a gas separated into two chambers, the removal of the partition leads to spontaneous mixing. Statistical mechanics tells us that the mixed configuration corresponds to far more microstates than the organized separated one. Analogy, it's like scattering a set of puzzle pieces on a table. While each piece could be reassembled into the final picture, the number of random arrangements far exceeds that singular original layout. The irreversible mixing paradox highlights an essential aspect of statistical mechanics. Information about the initial state becomes effectively lost as mixing proceeds. Even though the microscopic dynamics are completely deterministic, the practical inability to track every particle's path leads to an irreversible loss of information, manifesting as macroscopic irreversibility. Example, in turbulent mixing, any slight error in reversing the particle velocities, amplified by the complexity of the flow, means the exact initial segregation cannot be recovered. Analogy? It is akin to trying to unscramble an egg. While the molecules retain memory of their interactions in principle, the emergent disordered state is effectively irreversible because reconstructing the original order becomes statistically improbable. The irreversible mixing paradox is not merely a theoretical conundrum. It has significant practical ramifications in fluid dynamics and engineering. In microfluidic systems where control over fluid mixing is paramount, understanding how reversible microscopic laws give way to irreversible macroscopic behavior is key to designing efficient devices for chemical reactions, biological assays, and material synthesis. Example, engineers designing lab-on-a-chip devices must balance controlled mixing for reaction kinetics with the unwanted effects of irreversible diffusion, thereby optimizing performance for precise diagnostics. Analogy. It's comparable to adjusting the settings on a water mixer. While each droplet follows predictable paths, in theory, the combined flow leads to a consistently mixed stream that must be carefully managed for optimal output. Attempting to unmix fluids is fraught with enormous challenges. In an idealized reversible world, a complete reversal of fluid trajectories might separate the fluids. However, the practical impossibility of achieving perfect reversal, due to the extreme sensitivity to initial conditions and inevitable measurement errors, means that, once mixed, fluids effectively remain so. Example, laboratory experiments attempting time reversal in fluid flows have shown that any microscopic perturbation, no matter how small, derails the reversal process, confirming that the practical separation of mixed fluids is virtually unattainable. Analogy, it's like trying to reassemble a shattered vase. While each shard could be traced back to its origin in theory, the sheer number of pieces and the unpredictability of their paths render an exact reconstruction impossible. Understanding the irreversible mixing paradox continues to influence research across various disciplines, including non-equilibrium thermodynamics, chaos theory, and even the fundamental nature of time itself. As computational simulations and experimental techniques become more sophisticated, researchers are uncovering deeper insights into how microscopic precision gives rise to macroscopic irreversibility. These advances are likely to lead to innovative applications in material science, chemical engineering, and environmental science where controlling mixing and separation processes is crucial. Example, future research in nanoengineering may exploit controlled mixing at the molecular level to create materials with tailor-made properties, potentially leading to breakthroughs in energy storage or targeted drug delivery. Analogy. It's like uncovering the underlying score of a complex symphony. While each note can theoretically be reversed, the emergent melody and its inevitable progression towards harmony is a rich tapestry that defines the character and future potential of the system.